In this webinar, we're going to be discussing how to deploy and sustain additive manufacturing within your organization, and really a guide for additive transformation. But before we get into that, a little bit about ourselves and who we are. So we are Blueprint, and we are the world's leading 3D printing consultancy with over 15 or 16 years experience providing consulting to industry on how to adopt additive manufacturing. From strategy, service, and strategic consulting through to part design and application validation, we provide a range of services to help our clients make sense of 3D printing. We work across industry, from beauty and cosmetics through to energy generation. And over the years, we've developed a number of proprietary tools, methods, and software that allow us to help our clients understand, adopt additive manufacturing. And we also have gained a deep knowledge of the technologies across all 7 ASTM standards. And so we are a holistic 3D printing consultancy providing unbiased, technology agnostic consulting to our clients. But enough about us. To the point of this webinar, how do you deploy and sustain additive within a business? It's a pretty tall order for a 45-minute webinar, I'll grant you, and it requires a range of expertise. So we're going to take a three-pronged approach with the help of my colleagues. Myself, Oliver Smith, Senior Innovation Consultant at Blueprint, I'll be exploring the value of additive and why businesses need a new mindset to appreciate and leverage the unique value of this technology, and how can they build a business case. David Busaka, our Senior Engineering Consultant and Tech Guru, will delve into the complex world of material requirements and cost trade-offs, describing how you identify the right technology to fit your application. And Kunal Mehta, our MD, our Managing Director at the Blueprint, will demonstrate how you take this technology from experimentation and siloed initiatives in your business to real-world deployment across your entire organization. Our hope is, by the end of this webinar, through some case studies and us sharing our frameworks we've developed over the years, which we use in our consulting practice to help our clients, you will have a fully rounded guide for how you can fall back on when starting your additive journey. So let's start with the why. Why businesses need a new mindset to make the most of this technology and build a strong and robust business case. Well, back in the heyday of 3D printing media coverage, beginning of the decade, we had great expectations of this technology. We weren't just talking about product innovation. This was much more than prototyping. We were talking wholesale disruption to decades-long industrial paradigms around mass manufacturing, global supply chain configurations, the empowerment of the consumer, the rise of mass customization. In the 10 years since that now infamous Economist article, Print Me a Stradivarius, are we seeing evidence that businesses and organizations are applying 3D printing in the innovation that comes with it to grow their top line, strengthen their bottom line, and disrupt their status quo? The answer is yes. Additive manufacturing is indeed allowing a broad range of companies to increase growth and innovate products, as well as drive bottom line savings and lean their business operations. So one example here on the left-hand side is Unique. They're a medical device startup utilizing the power of customization and powered by 3D printing to upend the prosthetics market. By allowing patients to imbue a sense of identity into their prosthesis, they are turning them from items of tragedy into reflections of personality. And as niche as this market is, and it is indeed niche, Unique are not the only players. 3D printing has dropped the barriers to entry by such a degree that many other prosthetics providers, both new startups and incumbents, are entering this market because the economics have been turned on their head thanks to 3D printing. Conversely, if we look at Caterpillar, they are achieving dramatic savings across the board throughout their facilities in North America by applying 3D printing for all manner of applications, from jigs and fixtures to prototyping to even series production of some parts. Now, these are just two examples, but they are deliberate. They both describe the breadth of industries that are taking advantage of additive, from medtech startups through to decades-long conservative heavy manufacturing equipment providers. But they also show the very different ways in which additive is having an impact, from the creation of new business models at one end to the leaning of operations of companies that are multinational and decades old. But news-catching, feel-good, big brand stories and case studies can be deceptive. They can give us a false perception of the degree of impact this technology is having on our world. For all the talk of disruption, the AM industry as of 2019 is worth around $10 billion, and that's with a 30-year runway to get where we are today. For context, and context is always good to have, the consumer drone market is $6 billion and the smartwatch industry is $9 billion. Now, no one ever said smartwatches are going to trigger the fourth industrial revolution. So why are we at a par? For all the many examples of 3D printing driving innovation and efficiency, we're still seeing such a slow burn rate in adoption, and it's putting it at less than 0.03% of global manufacturing revenue. We're still not witnessing this boom, this new industrial age as promised. So what's going on here? Bill Taylor, co-founder of Fast Company magazine, prolific and critically acclaimed author on many business innovation books, said it best whilst he was at Rapid, the 3D printing trade show in Detroit last year. Walking the booth, he exclaimed, "You're not buying a piece of technology or hardware. You're buying into a new mindset and a new way of thinking, a new way of doing things." Essentially, 3D printing, as opposed to the vast majority of other methods of production, is still to a large degree an unknown quantity, and businesses aren't inclined to invest in an unknown. Let's put some figures behind this assumption. 200 CEOs across North America asked two questions about 3D printing. First, to what degree have they invested in additive, with 84% of them saying that they've not moved beyond prototyping, but they wish to. And second question was, what is preventing you from progressing towards further integration of the technology in your business? And 85% claimed that it was a lack of knowledge. This being the main barrier, not the usual suspects of cost, speed, and technology capability. The rules of engagement, therefore, have changed. And in order to understand how additive can add value to your business, the decision-making and value calculations used for conventional approaches to manufacturing, production technology, even business model design aren't sufficient. They don't stand up and they don't help us with this new technology. What is needed is a new mindset, or more to the point, a new framework that allows businesses to clearly understand the unique value of additive, what it has to offer, so they can start to build a more effective business case with this new and unique technology. One, however, that's based in strategic business value and not, as is so often the case, on interesting technological capabilities. At Blueprint, we use the 6 drivers framework as this new mindset. The 6 drivers are fundamental principles for how 3D printing can add business value. This forms the foundation of our consulting approach at Blueprint, and is what we use to help our clients rethink their approach to evaluating 3D printing, to give them a new mindset, not by technology capability, but by business value. And behind the 6 drivers are the 50 tactics, 50 ways in which 3D printing is allowing organizations to innovate, reconfigure, or streamline their products, processes, and business models. This framework can act both as a map and a menu. As a map, it allows you to explore and understand the landscape of 3D printing, what it can achieve, and how it can be implemented to drive growth and eliminate costs. But it can also be used as a menu of options for allowing businesses to assess, select, and combine multiple business benefits for 3D printing to form a more robust business case, and one that returns a higher degree of value for the same investment. So let's apply this framework to a case study that, as you'll see, is very well known, and see how we can use this framework. In doing so, demonstrate how it can be used to build a better additive business case. Now, I'm sure even if you've never heard of 3D printing, you would have heard about the GE LEAP engine nozzle. Everybody knows this story. A highly advanced design for an aircraft engine fuel injector, taking 8 years from design to production, that consolidated an 18-piece assembly into a single 3D printed unit. Clearly, the business case here was assembly consolidation of the number of parts. So it stands to reason that when GE designed their first clean sheet turboprop engine, the one used in the small Cessna aircraft, when designing the new engine in more than 30 years, they would build off the success of assembly consolidation. But the new generation of Cessna engines puts the LEAP engine nozzle to shame. Using 3D printing to redesign the engine assembly, they managed to bring it down from 855 traditionally manufactured components into just 12 3D printed ones, at a 98% part count reduction. But if we apply our new mindset, if you will, the six drivers framework, can we identify a larger benefit beyond assembly consolidation? Is that the business case, or is there more going on here? Now, no prizes for guessing that assembly consolidation is indeed a big part of this business case. As you can tell, bringing down 855 components to 12 or so, 98% of production, is going to have its benefit, from reducing the time it takes to assembly to minimizing the number of potential failure points in it, just as with the GE LEAP engine nozzle from several years ago. But is there more than just this? If we take a deeper look at the principle of freedom of design, one of the six drivers, and using the tactics framework, we can start to identify more at play here. So firstly, beyond assembly consolidation, they have been able to lightweight this engine by 5%. And in doing, they've been able to do this by redesigning components, reducing the number of total components, and miniaturizing systems, all through additive. But another more unique and quite often missed benefit of additive manufacturing in this instance is the application of biomimicry. Biomimicry is when designers copy patterns found in nature, because nature is the best designer. Now, the C-sump housing, the large conical component at the front of this engine, is covered in a lattice structure. And this lattice structure is actually inspired by plant cell structures, as they provide optimum strength to weight ratio. So in terms of freedom of design, it's not just assembly consolidation, it's part lightweighting and it's biomimicry. But there's more than just design at play here. There's also a supply chain component to this. Process displacement and supply chain compression. Essentially, big sentence, but essentially all that means is compressing the number of processes or suppliers you have in your production process. Now, what they've managed to do is internalize production of 35% of the components in this engine, reducing the serialized part count to just 35. Now, this is very much in line with GE's integration strategy they set out in 2016 to bring as many components in-house, either through additive manufacturing or other means, and taking them away from suppliers, both to increase speed of access to these parts, but also to increase security in their supply chain. But there's even more. It's not just supply chain reconfiguration. 3D printing allows us to produce very low volume number of parts, down to batch sizes of 1. And GE's turboprop engine utilizes this. By having a low volume production methodology, you can increase the design change responsiveness between batches without having to retool. Now, what this does is airframers, who are the customers of these engines, the manufacturers of small aircraft, can be more innovative in their aircraft designs and their aircraft fuselage designs. And GE can respond to those customer demands and provide better service and better product to them by tweaking and changing on the fly the design of the engine, because they haven't tooled up and they're not committed to a supplier. They can change designs between individual production runs. So this provides greater value to their customers. And finally, and what is often quite an overlooked benefit of 3D printing, is lifecycle sustainability. How can 3D printing improve the life cycle of a part, or the economics or the environmental impact of parts? Well, in this instance, there are three benefits, three tactics at play. Firstly, reduce life cycle impact of parts. Because this engine is so much more efficient, there's 20% less fuel burn, which has an obvious environmental benefit. But also, they've increased product efficiency with a 10% power increase thanks to the improvement of the system's design. And thirdly, they've designed this engine with design for repair in mind. So through assembly consolidation and better overall design, this enables more effective predictive maintenance, which is of value to the pilots or the owners of the aircraft. They can spend less money performing predictive maintenance. Therefore, the customer is getting added value from this product. So there we have it, very rapid, but a very quick disassemblement of this, what is often considered quite a simple business case, a simple application. So this new mindset, we can see that the GE turboprop is in fact far more advanced than it appears. By using the 6 drivers framework, we can clearly see that the success of this business case is not pinned to a single benefit of 3D printing, assembly consolidation. There are in fact 8 different benefits at play here, each adding additional value to the overall business case and improving the ROI, most importantly. And if we look at other examples of 3D printing across an array of industries, here is a smattering of very well-known brands who are using additive in quite a meaningful way. What we can quickly determine is that the most successful business cases are the ones that leverage multiple 3D printing benefits, advantages, to build a robust business case, not just leaning back on a single application or benefit, but tying in multiple applications and benefits to, as I said, build a more robust business case and improve the chances of a positive ROI. So here's the rub. 3D printing provides a range of new possibilities for businesses, from part design to supply chain reconfiguration. But conversely, many of these opportunities are still hard to quantify and difficult for companies to project a firm ROI. Like I said, the rules of engagement have changed, and there are a lot of unknowns still about how this technology integrates into businesses. So to improve your chances of success when investing in the technology, it pays to create a proposition that leverages as many benefits of additive manufacturing as possible, using the 6 drivers framework as a tool to look more deeply at how other businesses are applying this technology, understand the multitude of applications in their business case, and then recreate that success within your own business, as well as use the framework to start creating your own business cases, combining the many benefits that 3D printing has to create this robust business case. So to summarize some key takeaways for how you can build a better business case for additive and begin to adopt an additive mindset. They are: start by exploring the value, not the technology. The most common problem we find in our industry is that people start with technology capability first. Start with the business value and use the drivers framework to understand what that is. Secondly, question your status quo. This technology, as I said, it changes the rules of engagement within business and product and production design. We can do things that we could not do previously. So question your convention, question what you believe you couldn't do historically using this new technology. Thirdly, look enterprise-wide. Many of the benefits of 3D printing cannot be fully gained within one silo of the business. It's gained enterprise-wide. So look across your business and bring all portions of your business in when discussing additive. And finally, build a multifaceted business case, as I described with GE. The best business case are the ones that include and incorporate as many unique benefits as possible, as if when you get to the end of your deployment of it, several of these might not make it. They might not prove a positive ROI. They might fail because of engineering reasons. So you always need multiple benefits in case some of them aren't achievable. And with that, I'll pass to David Busacker to discuss how you make technology and applications fit.
Thanks, Oliver. Appreciate it. So before we go deeper, I just wanted to provide a reminder, like what we're doing here and the shape of this conversation. So Oliver just walked through the why, what we're doing, why you do it, how to establish a business case, a robust business case. I'm going to be talking about the what, and then following me is Kunal with the how. And I'm in charge of the what, like I said, but specifically we're talking about the technology. There's lots out there about what technology is, but I'm going to actually be talking about which technology to choose for a particular application. I'm going to be talking about application technology fit. So start by taking a look at this image here. It's 2020, so I finally feel comfortable revealing that this image tells a lie. You don't see any support material. You see multiple colors, and this is clearly a single extruder printer. And you're seeing a pristine final part. You're not staring at a ridiculously long build mid-print. You're not seeing any print failures along the side. And you could substitute this image with 100 others that we've seen. Every time you see a part being pulled out of a build chamber with no powder still left on it, picking up metal parts off of a pristine build platform, we all know that this isn't how the technology works. And I say that I can finally reveal this because we are seeing less and less of this kind of thing. Technology developers are finally starting to show real processes, real mess, the ugly side of 3D printing. The truth is, additive has something in common with every other manufacturing process. It is full of strengths and weaknesses. It can honestly be a pretty dirty, confusing process with lots of benefits, but with also lots of unforeseen complications. At Blueprint, we always tell our clients that AM should be considered a tool in the toolbox. But what does set additive manufacturing apart is the variety of these strengths and weaknesses, because there's a huge variety of technologies. In reality, additive manufacturing is approaching maturity as a technology, and typically that means technology convergence. But what we're actually seeing in the world of additive is a divergence of materials, processes, etc. Things are getting smaller, also larger, faster, but also more complex. There's just such variety among additive manufacturing technologies that you don't see in traditional manufacturing. Metal, plastics, ceramics when it comes to materials, different ways of making the parts, powders, lasers, inkjet nozzles, extruders, and for each there's strengths and weaknesses. So this technical variety really sets additive manufacturing apart, which is why it's so important to think critically with so many applications and so many technologies available. And that's honestly why Blueprint exists. We're here to make sense of additive manufacturing for the general industry. One of the ways that we do that is through our application technology fit framework. Whenever we recommend a technology for an application, we use this framework to explain our reasoning. And we're going to give you a little glimpse into how this works. It's called the app tech fit. That's 3 syllables. Application technology fit's a little too long. So I sometimes will abbreviate to app tech fit. The framework does 2 things for us. First, it provides a baseline for comparing and selecting a technology. And second, it exposes where more research needs to be done to establish confidence in an application. Both are super useful, as we'll see in a second. First, I want to introduce to you the technical principles, the think additively principles. These principles govern the application technology fit framework, and we use them all the time in Blueprint. When we teach our design for additive manufacturing courses, we center around these principles. Also, when we're talking about deploying an additive mindset in an engineering organization, these principles make a really good framework. So just briefly, the first one is color. What are the implications of part color, and does 3D printing uniquely enable full color parts, and for what applications? We also have surface quality, and what does surface quality and part texture do to the function of a part? And how do we carefully navigate additive's ability to impart texture to parts? We also have accuracy, thinking critically and creatively about how to achieve part accuracy, especially when it is not typically a strong suit of additive manufacturing. We also have strength, and what does a part need to be able to do? And what design freedom is available to trade for more strength? Finally, economics, and this is probably the most important one. What does a part really cost, and how to quantify and reduce a part's cost contributors? And this also plays into the business drivers that Oliver just went through for us. This plays into the economics of a part, but we'll get to that in a minute. So we'll use these principles in the AppTech Fit framework, which I'll explain next. As the name suggests, there are really 2 sides to the AppTech Fit. The first is application. And we'll go ahead and choose 3 very different applications. First, we have an aerospace bracket. We don't need to be more specific than that for now. We also have a thermoforming mold for clear aligners in the dental industry. And we also have a demonstrative anatomical model for use in hospitals and universities. We're going to stay really general about these applications, but what's important is they're different. And they're also very common. These are all very common. And the fact that they're both very different from each other and also very common additive applications is right there a suggestion of this technology convergence that we see. And for each of these parts, we're going to have what we call an application technical profile. So for each of those technical think additively principles I mentioned, there's going to be a set of priorities and requirements to achieve for each part. So for example, let's examine the requirements of the aerospace bracket. There really aren't any color requirements, so that's left blank. There's some surface quality requirements in that the stress risers can create strength problems in the part, but that's really ultimately a surface quality question. For accuracy, if the part's not repeatable enough, it won't be able to be airworthy. There's some strength requirements associated with the bracket, and there's also an established price target for this aerospace bracket, very common practice in the aerospace industry. So there's a variety of priorities and qualifications there. And I'm not going to read them for every single one of these applications. But the point is that anytime you're building something with additive, there are requirements and there's priorities that you're trying to establish with that part. And they can generally be pretty well described using the think additively principles. But as you can see, these different principles aren't necessarily always applicable to every application. For example, let's look at color. The aerospace bracket and the clear aligner thermoforming mold, really color isn't an issue at all. But when you get to that anatomical model, its entire purpose is to be demonstrative. So color is almost the most important principle there. So there's sort of a relative importance to these different principles among the applications. And it is important to quantify these technical applications as much as possible. But like I mentioned, sometimes these considerations are just priorities, not requirements. Like get that part as smooth as possible, or as strong as possible, or as light as possible. But at the end of the day, we use our experience in additive to qualify the requirements as high, low, or medium, or something in between. So what you're seeing here is a simplified version of the application technical profile. This simplified bar graph version of the profile shows us what's important to each of these applications and how relatively significant is that requirement. So we'll let the application sit for now, as we'll be using it in just a minute. The other half of the application technology framework is the technology. And as I mentioned, there are a lot of technologies. And frankly, it's getting impossible to name and perfectly categorize them. In fact, it's a fond pastime among some of the engineers in Blueprint to read about an emerging additive technology and then argue about which ASTM standard it really falls under. But a particular technology has a technology profile just like an application does. What truly is a technology though? The box that the powder sits in? Is it the powder itself? Is it the software running the printer? To effectively match a technology to our established application, we're going to need to clarify that technology. So to show you what I mean by clarifying a technology, we're going to continue through the AppTech Fit framework. So bear with me. Let's narrow in on the aerospace bracket for the rest of this demonstration. So we'll put that in the upper left-hand corner. Now, based on the established requirements of that bracket, most notably strength and accuracy, we need to create a short list of possible platforms. These platforms already have their strengths and weaknesses in general, as shown by the technology technical profile above. In the case of this particular bracket, polymer powder bed fusion and metal powder bed fusion have been shortlisted for comparison here. Note that aerospace brackets are also built using FDM, stereolithography investment castings, and other AM solutions. But for this particular bracket, we're narrowing in on powder bed fusion, metal, and polymer solutions. And whenever Blueprint explains technology selection to its customers, we also include an explanation of why we may have not chosen a peripheral technology. But a technology isn't just its base platform. It's also the material used in that platform. The attributes of a material will impact the technology profile as we adjust the strengths and weaknesses of that particular material. If you look at the effect of selecting a flame retardant nylon 11, you can see the effect, right? So there's going to be a little bit of a decrease in surface quality typically, as it's a little bit more difficult of material to sinter. You'll see an improvement in strength though, as nylon 11 is a fairly strong, robust material. And there'll be a little bit of a decrease in economics as well because there's more waste usually associated. So that's an example of how material will affect the technology technical profile. We don't have time to explore each effect, but you can see that this is a useful instructional tool. As is true of the platform shortlisting step, material selection and profile adjustment bring up really good opportunities for discussion and instruction. Okay, next, design. Design is ultimately part of the technology because it's the solution being brought to the table to address an application. Like a material, particular design decisions will affect the application profile. For the polymer solution on top, for example, adding ribbing will enhance the strength and accuracy, but diminish the economics as it is now a bulkier, more expensive part to produce, both in terms of post-processing and material use. For metal, using advanced design techniques will require more design labor, but it will improve accuracy and strength. Economics is a little bit of a wash due to the material usage reduction, but there's also going to be some labor involved in performing that generative design step. And the last dimension is access. Access is any business-specific contexts that are going to affect the feasibility of a technology. They include a lot of things, but they can include having a machine in-house or contracting through a service bureau. There's going to be pluses and minuses for each of those. Special in-house process knowledge, which might just make a technology more applicable to an application just because there's more known about it to the organization doing the product development. There's also partnerships with material or machine suppliers that might affect pricing or special access to expertise, existing budgets or technical commitments internal to the company, or centralization of manufacturing and other supply chain considerations that might affect the appropriateness of a particular technology. These special considerations will have an effect on the technical profile. So finally, we're going to bring the application back. Again, the technical discussions have been informed by the application all along, and this is crucial. But now we're going to bring the application back into view and compare to our final technical profiles and put them together to create our long-awaited application technology fit. We compare the application technology profile on the left against the technology technical profile in the middle to come up with a fit between our application and our shortlisted technologies. And for both of our shortlisted technologies, there is an app tech fit on the right-hand side we can look at. So what is going on here? The application is being compared to the technology, and the fit profile shows first where it meets requirements. So for example, color is just right on. There's not much color flexibility when it comes to powder bed fusion, and there's nothing really needed for the application. So that's a wash. There's also an example of where the technology is superior to what the application requires, and we call that a technical surplus. There's also areas where the technology does not meet the application, and we call that a technical deficit. And this is really useful because now we can use this to make future decisions. So where the requirements are met, that means the technology is a good fit, really nothing else required there. Where there's a surplus, that means that there might be some freedom, some design freedom that we can play with in order to further improve the application. And where there's a deficit, there's something we have to do further for it to meet requirements. Something that we need to do to bring it within what we sometimes call the sphere of additive capability. So from here on, our job is to get rid of those deficits if it's possible. I'll show you what I mean. Let's take a look at the metal powder bed fusion app tech fit. Surface accuracy right now is not being met. So one option we always have is to revisit the requirements. I really can't overemphasize the importance of revisiting requirements because a lot of the time they're not what they really need to be. Part requirements, especially on old drawings and specs, are frequently written because of how the part was made in the past. For example, if a part was put onto a CNC lathe and lathed down to particular diameters through a shaft, for instance, sometimes even non-critical surfaces will have really, really high tolerances or low tolerances for even if it's a non-critical surface. So re-examining requirements to make sure that it's really matches what the application needs to do is important here because it might save you really costly mitigation time for technology. But the other option is to use our technical surplus here. So we may switch our platform. Is there a more advanced, accurate powder bed fusion platform? For example, some of the innovations that Velo 3D is coming out with, improved software and hardware improvements. Can we switch the actual platform? And I'm not going to run through the material design and access that we have available to us here. But basically, these are our tools at our side to assist in these technical deficits. In this case, we're going to alter the technology by accessing a post-processing CNC operation. And this changes our technology profile. So we have taken a little bit of a cost hit. So our deficit for economics has actually become larger, but we've offset that accuracy problem. So like I mentioned, we still have that economics technical deficit. So let's see if we can do something about that. So it's kind of an iterative process. So again, our first option is to examine if there really is a requirement. And there's going to be a reason that I leave this option highlighted in orange because I will come back to it. But let's say we want to convert a technical surplus into our deficit for this example. In this case, we're going to do a couple of things here. There's a few levers we're going to pull. The first one is that we're going to try to reduce our price by bringing down the machine cycle time by changing laser speeds. This will probably reduce our surface quality though, so that's going to have to be accounted for in our technical profile, as now we're melting more metal faster than ever. We can also remove some more metal from our topology optimized design at the expense of some part strength, which is a surplus right now. So we make the appropriate adjustments to our AppTech fit, and we can see the results. So this is the application technology fit framework. Again, it has two really important purposes: to explain why a technology is chosen for a specific application, and also to serve as an instructional framework and demonstrate areas that need more examination or research. Hopefully, as we talk through this exercise, you had a dozen questions or a couple dozen questions that I didn't have time to answer. And that's actually the point of the framework. It's used to expose real questions and caveats. In the case of diverging technologies that make up additive manufacturing, there are probably 5 caveats to any given rule we try to put out there. So it's important to use frameworks like this to frame application-specific conversations and decisions, because the answer is almost never cut and dry. So I'll leave you here with this completed application technology fit profile. But one last thing. You'll notice that there's still that economics technical deficit. The price of this metal part is still higher than the price target, which is why I want to re-examine whether the price of this part is truly a constraint. So that question there in orange, is this the only economic consideration here? We think maybe a little harder about the financial implications of this part. And ultimately, the answer is often yes. A more expensive part is often perfectly acceptable with additive manufacturing. But to talk more about thinking bigger about additive value is Kunal Mehta, the Managing Director of Blueprint. Kunal?
Thanks, David. As Ollie mentioned at the beginning of the session, my name is Kunal Mehta, and I lead our global Blueprint team. David did a great job making sense of what is unique in our industry. Different 3D printing solutions are best suited for different applications. The goal, of course, is for that AppTech fit that David mentioned to be green across the board. But is this always true? With today's technologies, you often can find a match for color, for accuracy, for strength, for surface quality, as described by David. And while there are cases where the piece part cost of the application is cheaper than traditional manufacturing, reality is we often see cost neutral, if not cost negative 3D printed parts. Obviously, this doesn't help us justify 3D printing. It makes our jobs much harder when we're convincing our clients the value of 3D printing. So how do you address this piece part cost? Where most folks think about this, who is printing the parts? Either you can purchase capital equipment or use an external vendor or service bureau. This is often called the make or buy decision. If you're new to additive, starting with a service bureau likely makes sense. While the piece part costs may be at a premium, likely 20% or more, this allows you to experiment and allows you to dabble with additive without the upfront capital. Of course, as you move to the right, this means an increase in additive adoption, which also means an increase in capital expenses, but will lead to lower piece part costs. So is all really lost? Are we stuck with higher piece part prices? Maybe. But remember, the value of 3D printing is not to do with the price of the part. It is so much more, as Ollie mentioned when we spoke about the business drivers. Now that you've gone ahead and found the application technology fit, likely have designed your part, double back to the business drivers and check if they're still valid. Maybe you started with 6 tactics and 4 drivers, but during the process, 1 or 2 of those tactics was not achieved. That's still fine. You still have 4 to 5 to focus on. The key to additive adoption success is quantifying that business driver, quantifying the success of the ROI. Do you do the hard work to understand the dollars saved, the efficiencies gained, potentially the revenue created by using additive? We recently worked with Massachusetts Bay Transit Authority, Boston's Transit Authority, or T-Service. They had a hard to source light fixture that was critical for the car to be back in service. While a 3D printing solution was 3 times the cost of traditional, which is quite a bit more, we identified a 14-week lead time reduction. Working with the client, we determined that each day that a rail car was out of service resulted in $15,000 to $20,000 in penalties, which is roughly $1.5 million over 14 weeks. That's a lot of money. Additive became a prime solution. Procurement, purchasing, inventory, all of the folks quickly understood that their traditional way of thinking about sourcing would have to be changed. It wasn't easy. It required thinking outside the box. It required a mindset change. And to be honest, it'll require a business model change. So to close, the main question we ask our customers, does the value of the tactics offset the piece part cost? If you need help defining this, reach out to us. So now that we've talked about the why and the what, let me take us home and talk about the how. How do we determine success? How do we deploy this technology into an organization? Like most new technologies, most of our customers go straight on focusing on the supply chain. They focus on getting the technology in-house, in our case, the machines, the materials, and setting up the infrastructure. But this is often the fatal flaw of deployment and adoption. So where do you start? Based on our collective experience in projects with Fortune 500s, with startups, with governments, etc., we've developed a 5-pillar framework to assess each component for successful adoption. We start by answering stakeholder questions and reaching a consensus on the desired results and impact of 3D printing. How does this technology align with your overall business strategy? If you're a large military OEM, where does additive play in your org? Does it start with product design, or does it start with sustainment, or do you do both? These decisions need to be made in a larger context of your overall business strategy to ensure you have focus and the prioritization needed for additive. Secondly, ensure that you have a governance model in place to ensure alignment, oversight, and investment as additive is part of your new strategy. Is additive being driven top-down? Is it being driven bottoms-up? Is it across multiple organizations? Do you have champions across these organizations, or is it hidden in a specific lab? What KPIs are being tracked for additive adoption? Someone or some entity needs to track this regularly to hold the organization accountable. Then you get a bit more tactical, specifically focusing on the people supporting your strategy. Are you set up organizationally? Do you have the right skills? Are you ready culturally to take on this new technology? People are important. In the end, you need your engineers and designers to think additively to effectively utilize the technology. Next is ensure you have the right processes and systems in place. Can you tactically execute additive? Do you have the right operational support in place? Do you have the right design software? Do you have the right software? Are your 3D printers connected to your MES systems? All of these questions need to be answered in terms of processes and systems integration. And then, finally, at the end, focus on machines, materials, sourcing, and infrastructure. So while all of these do not have to be done in a stepwise motion, you need to consider each pillar to recognize the long-term success. There's an interplay between each of these pillars, and in general, the level of depth in each of these light gray boxes on the right side changes based on your maturity of additive. If you're a design studio with the likes of IDEO or Fjord, using 3D printing for prototyping, you likely have less processes, you likely need less processes, and you don't have a need for various systems integration. On the other hand, if you're an aerospace OEM, such as Boeing or Lockheed, you'd want to incorporate the same stringent and necessary processes to produce parts, as well as some form of digital threading through your supply chains. Our recommendation is use this framework as a starting point. Depending on your goals, assess each box, and ask the questions on how much depth you need to go into. Approach additive holistically. This is probably the most important part. For additive to be transformational, the entire business must buy into additive. This means from the boardroom through to the factory floor. Over the course of this session, we've shared numerous cases of needing a new mindset. First, thinking about the business drivers, then how the applications and technologies fit, followed by quantifying the ROI, and finally, a framework for actually deploying it. So to close, one final thought. The world is changing, from how products are manufactured to how customers engage with products and companies. The past is a very linear model, and that's no longer the case. In our world, in this old world, manufacturing was linear. You figured out what you were developing, you picked the right technologies, those technologies actually inform design, and then you manufacture and ultimately sell and use it. With additive, we're no longer linear. Manufacturing actually can be continuous, it can be dynamic, and it can be very iterative. And the need to be more resilient is ever more prevalent today. It's been brewing in the background for years due to trade wars and the like, but COVID-19 today took the covers off, showing how fragile our supply chains really are. We have the option of this nonstop design. And ultimately, we can act quickly on value manufacturing and technologies. This is the beauty of additive. And don't be disheartened. Start, try, pilot, experiment. You might fail. You will fail, but learn from it. AM allows an efficient and effective iterative process, unlike any other technology out there. Traditional is very defined, so for now, utilize the unknown of additive for your benefit. In the spirit of a new mindset, we have 2 education opportunities we offer to customers. Firstly, our Think Additively program. This is targeted towards engineers and designers. It's our Design for Additive Manufacturing course that typically takes 3-ish or so days at a customer site. Given the current environment, we likely are pushing our in-person session event scheduled for June. However, we do have a mini digital session scheduled for April 13th to 17th. It's 1 hour each day for 5 days straight. We plan to go through our 6 business drivers a bit more in depth and the 5 additive principles that David mentioned. To register, go to additiveblueprint.com/thinkadditively2020. Separately, we also host an executive level workshop called the Additive Accelerator. The point of this is to help our leadership teams, your leadership teams, understand the value of additive. But more importantly, work with your executive teams to identify where additive makes sense in your business and create an action plan that you can tactically move forward on. This is planned for Q3, closer towards IMTS. So if you're interested in both of them and have questions, please reach out to us at hello@additiveblueprint.com. And lastly, as Blueprint, we love sharing information and educating our customers. Last year, you may remember that we launched our Little Blue Book of 3D printing. This book showcased our 50 tactics with real examples. This year, we wanted to create a blueprint for 3D printing, building a how-to guide for building your additive strategy. This book plans to outline a couple of things: how AM adds value across prototyping, assembly, manufacturing, sales and retail, and aftermarket, the 5 stages of a product lifecycle. We share 15 different configurations of incorporating additive into your organization, 5 frameworks to help you select the right technology, 50 questions to prioritize the value of AM, and like the Little Blue Book, we showcase 45 case studies to get you to think. So as a teaser, here are the 45 case studies we plan to share, from the likes of Google to WeWork Labs to Bombardier, Adidas, Nespresso, Gillette, Bosch. There's 45 on here. Get excited because we certainly are. More to come at the end of April. And again, if interested in a copy, reach out to us. So for more content like you saw today, go to our website, specifically our thinking page. The webinar will be posted there along with dozens of other blogs and webinars that we've hosted in the past. And to conclude, thank you for your time. We hope you enjoyed the presentation. If you're interested in chatting, again, drop us a line at hello@additiveblueprint.com or give us a ring. We look forward to hear from you. And finally, I wish everyone good health and safety in these crazy times. Thank you so much.